The next topic is coefficient of multiple determination R squared. So here this time we're going to call this multiple determination because this is multiple regression analysis. In the previous chapter, the terminology we used for R squared was coefficient of determination. So now we say coefficient of multiple determination, and the formula is the same, SSR over SST. So regression sum of squares divided by the total sum of squares, and the interpretation is same as well because it measures the proportion of total variance in the y values. Okay, that is explained by the regression. It's no longer a variance of y anymore after we fit the regression. So this amount of variance is now explained away by the regression analysis. So R squared again is a value between 0 and 1. Closer to 1 means that it's perfect relationship. Closer to 0 means it's not very good. So here is how we calculate R squared. So when we run an Excel regression analysis, and here is the regression analysis results. Okay, so this is our SSR, and that's our SST. So divide SSR by SST and we get R squared, and of course Excel regression analysis results gives us that information in the top summary statistics, so which is right here. And the interpretation is 52.1% of the variation in pie sales is explained by the variation in the price and the advertising. So that's the regression analysis. So in the case of multiple regression, we can calculate one more measure, and that is called adjusted R squared. And the reason for computing adjusted R squared is as follows. The regular R squared, the coefficient of multiple determination, will never go down as we keep adding more x variables into the model. So let's suppose that we already have like 3 variables in the model and we have R squared of say 70%. If you add a 4th variable in, the R squared will always go up. Either it will go up significantly or by a small amount, but it will always go up. So adding one more variable in here, whether it is a good thing or not, it cannot be determined by simply looking at whether R squared has gone up or not, because it will always go up. Whether the additional variable that we are including adds any value to the model or not, R squared will always go up. So this can be a disadvantage when comparing models. So what is the net effect of adding a new variable? So when you add a new variable, the degrees of freedom for error goes down by 1. So that means the denominator for mean square error decreases by 1. That means there is a tendency for the MSE to go up. In the modeling analysis, we want to keep the MSE value as small as possible. So by adding a new variable, okay, the denominator goes down in the calculation of MSE. So that puts a pressure for MSE to go up. But of course, if the new variable that is coming in significantly reduces the numerator, sum of squares of error, so that is this new variable makes a significant contribution to reducing the variance of y, so then the numerator will go down sufficiently to more than offset the loss of the degrees of freedom. So MSE will go down. Okay. So once again, when we add a new variable, we lose the degree of freedom. So to compensate for the degree of freedom, we want to see whether the new x variable adds enough explanatory power to offset that loss. And that's what adjusted R squared does. Adjusted R squared, calculated with this formula, takes into account both the loss of the degrees of freedom and that is the disadvantage, and the benefit of adding a new variable in terms of the explanatory power. So you've adjusted R squared increases, so then that is a good thing. So that's why we compute adjusted R squared. So here is adjusted R squared from Excel output. Okay. Now let's compute the adjusted R squared value for our Excel example. So we're going to compute both R squared and adjusted R squared. R squared value is SSR divided by SST. Of course, that's going to be equal to this R squared value, which is 0.75773. So we'll put that as a percentage. Okay. So that means 75.77% of the variance in sales is explained by the regression analysis or the regression equation. Now we want to compute adjusted R squared, and for that we need N. Okay. So N is observations. Okay. K is the number of variables, which is 2. So adjusted R squared, okay, we use this formula, is equal to 1 minus, okay, 1 minus R squared, which is that, okay, times, so we have two things now, N minus 1 in the numerator divided by N minus K minus 1. So then we need that. So that's the adjusted R squared, and that's equal to the adjusted R squared Excel generates, which is that one. And you see it's the same number.